It's math time with Heinz. It's math time with Heinz. Math time.
Hi everybody, welcome to lesson 3 here, where we're going to continue exploring ways to solve systems of equations. And we're going to talk about elimination in detail today, which is something you learned last year how to solve a system with elimination. We're going to go over that again. So Joey claims that 1, 5 is a solution to the system below. Determine if Joey's correct. So how do I check if this is a solution? Well, we plug it in. X equals 1 and y equals 5. So let's plug that in wherever I see x and y. So 4 times 1 plus 2 times 5 equals 14. Well, 4 plus 10, that does equal 14. But it's not a solution to the system because it has to work for both. It works for the top equation. I now have to check the bottom equation here. So x minus y equals negative 4. 1 minus 5 is negative 4. So since it works for both, it's a solution to the system. So since 1, 5 makes both equations true, it is a solution to the system. So since 1, 5 makes both equations true, it is actually a solution to the system. Well, what if I was to add these two equations together? So if I take these two equations here and kind of smush them together, if I add these two equations together, I'm going to get a new equation. So let's see what happens when I smush these two equations together. So 4x and 1x gives me 5x's. 2y minus a y gives me 1y, and that equals 10. So I get this new equation here. Does 1, 5 work for that one equation? Well, let's check. 5 times 1 plus y equals 10. Well, last time I checked, 5 plus 5 does equal 10. So adding equations together doesn't change the point that's a solution to both of them. So if I was to graph these two equations here, so I had 4x plus 2y equals 14. Let me go on projector mode for a second. So there's my first equation, and my second equation was x minus y equals negative 4. We'll notice that the solution to the system, the point of intersection of those two linear functions there, is 1, 5, which we expected. And now we've got this new equation, 5x plus y equals 10. And what do we notice about that green line? That green line, if added to that system of equations, still has the same solution. So if we add equations together, we can preserve the solution to the system. So that's what we're going to do when we eliminate, is we're going to end up adding equations together because that's a legal thing to do. It doesn't change that solution to the system. What if I multiply the equations by a number? At this point, I'd ask someone what their favorite number is, and someone would probably say, 5. So let's take that top equation there and multiply everybody. Let's scale this equation up by a factor of 5. So what's my new equation? 20x plus 10y equals 70. So here's this new equation. Let's graph this and see what happens. So let's graph this. So it was 20x plus 10y equals 70. So I need you to see what happened there. Look what happened. I had this purple line as my new line there. But notice it covers up this red line here. So this purple and red line are really the same. So by multiplying it, we change the way it looks without actually changing the function. We change the way the equation looks. We change the way the equation appears without changing the line. When we add them, we're actually changing the line. But at this point, it's just making the equation look different without changing the line. So it's still the exact same linear equation. It just looks different. So is 1, 5 still a solution? Yes. You could pick whatever number you want. I could have picked -5. I could have picked 20. I could have cut them in half. Notice I can cut everybody in half here. Cut in half, cut in half, cut in half. I'm still going to get that exact same line. So if I cut that in half, go away, plus y equals 7. Notice, plus y equals 7. Notice the black line covered up the red line there because it's this, and now the purple line. They're all the same line because they're just multiples of that same equation. I could have picked whatever number I wanted. I could have done 3. 12x plus 6y equals 42. As long as I multiply everybody by that same constant, that same number, we're good to go. So what we're going to do is we're going to rig the system here so someone eliminates. So I'm going to rewrite the system using this idea of adding them together and setting it up so one of the variables eliminates. We can solve this system. So here's what we're going to do. We need opposites. When we use elimination, we need opposites. What does that mean? I've got 2y, and I also want -2y, because when I add those together, they eliminate and become 0. They don't go to nothing. They become 0. So here's what I've got to do. I've got 2y. How do I make this a -2y? Well, I've got to scale it up by 2. I already got the negative. So I didn't touch the top equation. In the bottom equation, I'm going to double everybody. Double, double, double. And that was a legal move to do there. Now when I add them together, those will eliminate and become 0. So I'm left with 6x equals 6. So x equals 1, as we knew, but I haven't finished solving the system. I've got to plug it back in. 4 times 1 plus 2y equals 14. 4 plus 2y is 14. And now I'm just solving this nice two-step equation here. And I get y equals 5. So just like substitution, you've got to plug back in to get the answer. But with elimination here, it's a little bit different process. You're not plugging something in for something else. You're rigging it up. You're setting it up so that you have opposites that add to 0. And then you can smush the equations together through adding, and you're good to go. So the solution here is 1, 5, which we knew 7 minutes ago. All right, let's practice this idea of elimination. So let's look at this first one here. 8x minus 6y equals 30. 9x plus 6y equals 21. Well, I know I'm not substituting because I don't have a variable that's hanging out alone. If I had a plain old y equals or x equals, I would use substitution. But here, I'm going to use elimination. So I'm going to check, do I have opposites? 8x and 9x? No, those aren't opposites. Negatives, I do have opposites here. So this is ready to go for me to just smush these equations together column-wise. 17x, those we say goodbye to. Goodbye, goodbye. And we get 51. We added everybody together. And then I'll divide. And 51 divided by 17 is 3. We're not done yet. We've got to plug it on in. Doesn't matter, top or bottom. I'm going to go top. You're going to get the same answer either way. So 24 minus 6y equals 30. Solve in a way. Negative 6y equals 6. So y equals -1. So these two lines intersect at the point 3, -1. I added them together because I already had opposites. That's not how it's going to be set up most of the time. Most of the time, you're going to encounter problems like this where you don't have opposites. 2x and 6x, 4y and 3y. So you've got to decide which variable to eliminate. You can always eliminate either one. I think it's easier to deal with 6 and 2 because I'm going to turn this into a -6. How? By multiplying by -3. So I'm scaling that top equation by a -3 times -3. Don't forget the plain old number times -3. All right, here we go. Now I've set it up so I can add them together. -9y equals -9. So y equals 1. That's why I still need to solve for x. So 2x plus 4y equals 2. 2x plus 4 equals 2 minus 4. And then I divide, and I get x equals -1. So always be careful. X comma y is the point of intersection. So here I had to multiply one of the equations by -3 to make sure I got opposites. If I was dealing with 4 and 3, what can I multiply both of those up to? Well, I'd have to multiply both of them, so I get 12. All right, -x plus 2y equals 11. 5x plus 2y equals 29. Well, this is nice, but they're not opposites. So you've got two choices here. Your first choice was to multiply this by -1, or the bottom one. Doesn't matter. One of them had to be multiplied by -1, so that way you have opposites. So change the sign, change the sign, change the sign. I didn't touch the bottom equation, so now I can add them together. 6x equals 18, so x equals 3. Now I could plug that back in, but I'm going to show you the other way we could have solved this equation. The other way we could have solved it was to eliminate the x's. So what we could have done here was multiplied this top one by 5, because I have +5, and this would cause that to become a -5. Make sure you're multiplying everybody. And then I can add these together. Now I get 12y equals 4, carry the 84. And dividing by 12, I get 7. Which I got ahead of myself there. Y equals 7. So notice I did elimination twice here. I don't recommend doing that all the time, but if you'd like that, that's fine. But there's more than one way to do these problems is what I want you to understand. So just because I did it one way, you might do it another way to get to the solution. This next one here is worst case scenario. This next one here is worst case scenario. I haven't used, what color haven't I used yet? I did green, I didn't use purple yet. So worst case scenario here, I've got a 5 and a 2, those aren't opposites. A 2 and a 7, those aren't opposites. So I've got to multiply both of them. And here's your choice. What can I make 5 and 2? What is their least common multiple? Well, that would be 10, right? I can make both them 10. Or I could do, one would have to be 10, one would have to be -10. Or I could deal with my y's. I got 2 and 7. I can make those 14. One's already negative, so we're good there. But you have to make sure that you can scale them up to the same number, and one of them's got to be opposite. I'll deal with 5 and 2. So I'll make that 10. And I'll make this one -10. Doesn't matter where you put the negative. One of them's got to be negative, so they're opposites. But in this case, you have to multiply both of them. So top equation, times 2, times 2, times 2, times -5, times -5, oh boy, times -5. Yes, I did that right. So now I can add them together and get -39y equals -115, I believe. I believe it's -115, which, when I divide them, hopefully this divides nicely here. No, what did I do wrong? 43 times 5. Ooh, that was really bad there. That was terrible math, Heinz. I don't even know what I did. Don't do what I just did. -215. Ouch. Bad, Heinz. I have to hit myself on the face there for that. 215 and 20 make -195. That was bad mistake there. Always use a calculator is the moral of the story. So I get y equals, using my calculator again, 2 negatives divide to a +5. Okay, so notice how sometimes the numbers get rather large, and that happens sometimes, so use a calculator. Let's plug back in. I'm going to use the bottom one. Why? I don't know. There are no negatives in this one. (2x equals 8). So x equals 4. So 4, comma 5 is the point of intersection. All right, so hopefully this was a good review. We got 2 more questions to do, and then we'll call it a lesson. So which system of equations has the same solution as the system below? So as like a multiple choice question, I might ask you something like this. Now, I don't want you to solve all of these because that's insane. I want you to use your eyes and look. Here's the starting. Here's the equation 1 and equation 2. Let's look at this new system here. 2x plus 2y equals 16. That matches up perfectly. But the bottom doesn't match up. So how do I go from the bottom to here? 3x times 2 times 2. Ooh, that's not times 2. That should be 8. So does that have the same solutions? No, because it wasn't multiplied properly. That's what we're looking for here. All right, top equation didn't change. Let's look at the bottom equation here. Times 2 times 2 times 2. This one looks good to go because it's the same top equation, and this guy just got multiplied by 2. That's all that happened there, is he got doubled. Let's see what's wrong with these other guys here. Cut in half, cut in half. Ooh, that should be an 8 there. If you cut one side in half, you got to cut the other side in half. And then that bottom equation was actually fine because it's the same. And then this last one here, let's see what went wrong. 2 became a 6. 2 became a 6. So it's times 3 times 3 times 3. That's actually good because that was just a times 3. Let's see what goes wrong on the bottom. Times 2. Oh, that should be a negative 2y, not a positive 2y. So that's where this one went wrong. That's why it doesn't have the same solutions, because it's not the same line. This is the same line. Remember from the beginning, it's the same line. It just looks different. It just covers up the exact same line just because it has that multiplier happening between them. Okay, so when you see a multiple choice like this, don't solve all 5 of them. That's insane. Just look. Use your eyes and see, how did I get there? What did I multiply by? Did I do it correctly? All right, finally, we got a small movie theater here. They got children's tickets for $4 each and adults for $10 each. The theater sells a total of $388. So write a system of equations. So that means I need 2. I need 2 equations here. So let's deal with the money. I like to deal with the money first and get that out of the way. $4 a child and $10 for each adult gives me $388. There's all my money. $4 a kid plus $10 an adult gives me $388. Then I tell you there's a total. This is your separate equation. This is your total equation. Your total equation has nothing to deal with money. Children plus adults has to give me 70. This is your total. So when we write systems of equations, this is one popular setup of a problem where you have a money equation and then you have a total equation following it. Determine how many children and adults are at the movie. Well, let's solve this system. So you can do substitution here if you move that A over, right? If I move that A over, but let's do some elimination here, and I like doing elimination. I've got 4, so let's multiply by -4 to make opposites. All right, so I didn't touch the top equation. Can't touch this. And the bottom one's getting a -4. Everybody's getting -4. There, I can multiply. I did it right this time. Those make 0. 10 minus 4 is 6. And that gives me 108. So I need to divide by 6, and I get 18. There were 18 adults there. I think that's a lot faster than doing substitution. I think elimination's a lot faster because I can easily make opposites by multiplying by -4. Which one am I going to plug into? I'm going to plug into the easier one. Children plus adults gives me 70. If there's 70 kids, you can kind of just think about this in your head. If there's 18 adults, how many kids are there? Well, it has to be 52, because 52 plus 18 gives me 70. All right? So hopefully this was a good review of elimination. I'm sorry this video got a little bit long, but it's a good skill that we're going to be practicing in class.